we were discussing about operational amplifier introduced errors for DC application. So, there are various errors which we have discussed earlier. They are offset voltage drift error, the bias current drift error, then input impedance error, output impedance error, then CMRR introduced error, and then the gain drift error. These are the errors that we have listed earlier. And then we also discussed about what is the issue with offset voltage drift, and then we also shown one worked out example because of the offset voltage drift how the error was coming and what is to be done. Then next we discussed about bias current error, and because of the bias current that is flowing into the terminals of the op amp, there is a DC error at the output. Then how to reduce that, that is what we were discussing in the previous class. We continue that in this class now. So, the bias current error is what that we are going to discuss in detail today, bias current error. So, what we had done in the earlier class was that to remove the bias current error, that the suggested method was that you have the two gain resistance here, say RF and then R1, and then the plus input what we are giving the input voltage, and we add for example one series resistance here. There is one possibility, or even before going into that, for example, if I can look without the input, what we can do is that you have the input voltage here. Assume there is no input voltage, then I suppose to get 0 output voltage, that we can achieve by putting this resistance RB, because of a bias current we had shown earlier, because of the bias current that is flowing into the input terminals of the op amp, that current actually flows through this from the output, it flows into this, and then this flows into this, and then we are assumed I minus equal to I plus. If I minus equal to I plus, then if I add this resistance, then this current also flows this, I plus is flowing here, then I minus is actually flowing here. This is basically I minus this current. So, by adding this resistance, we were generating minus voltage. So, by adding RB, negative voltage is introduced at the non-inverting input. So, this negative voltage is compensated by the positive voltage introduced by the RF. So, the bias current that is flowing here, bias current that is flowing to this terminal produce a positive voltage here, and the bias current flowing through this produce a negative voltage at the output. So, to compensate that, we have to make the output voltage equal to 0. So, that means if I take RF, if I take RF into I minus should be equal to RB into I plus to come. That will make the output voltage equal to 0, there is no error due to the bias current. So, if I that means if we assume here we assume that the input voltage is RB into IB is the input voltage. Of course, this is simplified by 1 plus gain. So, we had if I had to do this, I had to put 1 plus G here, because the whatever voltage that is applied here is amplified by the gain, that is 1 plus RF by R1, and that is produced at the output. So, if you continue this, then it comes, that will be RB into I plus, then you will get 1 plus RF by R1, that is what you will get this. And if I equate I plus and I minus, then soon you will get RF will be equal to R B into 1 plus R F by R 1. That will make, because we want to know R B, that what is to be connected there to what is to be connected at the non-inverting input to compensate the error, that will make R B will be equal to R F by 1 plus R F by R 1, and that on simplification you will get this one R F into R 1. So, R B will be parallel combination of R F and R 1, because this is nothing but appears as a parallel combination of R F and R 1. That means R B value that is to be selected such that that is parallel combination of these two is added here, that gives output voltage 0. Here the assumption is that R 1 is the assumption is I minus equal to I plus, that is the two bias currents are equal, but in a actual case they are not equal. So, now we have to worry next what happens if the two are not equal, because if the two are equal, then one can make the parallel combination of these two resistors can be put here, then one can forget about the bias current effect. But unfortunately that I plus and I minus are not equal, and they are also changing with the temperature. So, that means we have to find out what is the net output error if I minus equal to I minus is not equal to I plus. So, if I minus is not equal to I plus, in fact this is the real case, this is the real life situation, this is the real life situation. So, how to reduce the error? So, what you do is assume I plus minus I minus, difference as I offset, we call offset current, I offset current. So, the difference between the two currents we call it as a offset current. So, if offset current is the quantity that is given by most of the operational amplifier manufacturers. So, if I know offset current, then I should be able to find out the error. So, if the offset current is known, then what is the error? If offset current is known, then what is the error? That is the question. So, if it is known, then if you look at the circuit again, that you have the two resistance here, then assume that I have put here RF and R1, and let's say it is a 10K and 1K. Then the parallel combination of these two will be 1K parallel 10K, roughly 1K. You will be getting it here. So, close to 1K will be the resistance that you will be connecting here. If offset current is I offset is there, then the extra error that is coming here would be then V output error is equal to I offset into RB into gain, because we can assume that this the plus current is more. One easiest way of solving this would be assume this current is more and then this current is less, then I can assume that this, since this resistance is put parallel combination of these two, which makes the output 0. So, I can neglect the from I plus, I can subtract I minus and assume that only that much current is flowing here. So, we can say now that net current flowing here would be only the offset current into this resistance will be the error voltage at the input multiplied by the gain is the error voltage at the output. That is how that this equation had come. So, the error voltage V0 error voltage, that is the error voltage at the output voltage at the output is equal to voltage, error voltage that is I offset current into RB into gain. Now, this offset current, it depends on the operation. For example, if I take 741, then offset current error is given as per 7, for example, for 741 op amp, I offset current, for example, is equal to about 1 nanoampere, for example, the 1 nanoampere. So, if I have 1K resistance, then you will have only 1 microvolt. But if you for 741 it is around 10 nanoampere, whereas if you take bias current by itself, they are at 50 nanoampere level. So, the offset current is much smaller. So, the error induced by the offset current is smaller if the resistance values are small. So, if it is if the gain is 10 and if I had used 1K and 10K, then the error would be V0 error would be 10 nanoampere into 1K into gain 10, that actually amounts to 10 power 10 power minus 4 volt at the output, that is 0.1 millivolt error at the output that it gives because of 741. If I use gain 10 with 1K and 10K combination, whereas if I go for higher resistance, then the error comes very high. For example, if I set a circuit that is the same gain 10, for example, I go for 9 meg and then 1 meg, which gives me the gain 10, then I put this, which will be 1 meg, then the error would be V0 error would be 1 meg into 10 nanoampere into gain 10. So, that will be 10 power 6 into 10 power minus 8 into 10, that is 0.1 volt. So, the error voltage due to bias current increases with the resistance that is used to set the gain. So, higher the resistance, then we have more problem due to bias current. Actual problem is not the bias current or offset current. This offset current is not constant. So, the offset current changes with temperature. This is the major problem rather than the offset current. So, the actual problem is the offset current is not constant. It is changing with temperature. It is changing with temperature. This is called offset current drift. Offset current drift is more problem. Offset current drift is the problem. Current drift, offset current drift is a major problem. It's a major problem and not the offset current itself. By itself. So, offset current by itself is not a problem, but the offset current drift is the major issue. So, this offset current drift is a major issue next to offset voltage drift, because offset voltage drift is independent of resistance that we are using, but offset current drift depends upon the resistance that we are using. So, we at this one, that is offset voltage drift. Offset voltage drift is a major problem. Is a major problem, and it doesn't depend upon gain resistors, gain setting resistors. Now, the offset current drift, the offset current drift is also a serious problem, and it depends on the gain setting resistors. So, one must aware of these two problems, that is offset current drift and offset voltage drift, and these two are the main limiting factors in operational amplifier applications, that is for the operational amplifier DC applications. In AC applications we need not worry about these parameters. If you are using operational amplifier for DC applications, then one have to worry about these two parameters, offset current and offset voltage drift. Now, is there anything that one can do to remove the offset current drift or offset voltage drift? What is that one can do? What is that we can do? To reduce the offset current drift. Now, other than what we are trying to do is, other than reducing the resistance values in the feedback network, what else that we can do to reduce the offset other than reducing the resistor values. Now, actually only choice that you have is go for low bias current or low offset current, op amps like FET input op amps, FET input op amps. So, if I use a low bias current op amp, obviously offset current also will come down, offset current drift also will come down. For example, FET input op amps are the good choice to reduce the error due to the offset current, because for example, if you compare 741 where offset current is 10 nanoampere for 741 offset current is 10 nanoamps. Now, same thing FET version available for 741, there is 741 which is FET input op amp. The offset current is 10 pic amps. There in pic amps say about 3 orders of magnitude less, that is about factor of 1000 less. So, the offset current drift also obviously comes less, and the error introduced by that also will be less. So, if you want really working with if you really want to use a very high resistance values, then one have to go for FET input op amp. For example, we take pH meter amplifier, then we can understand the issue with the offset current much more easily. So, for example, take a design of pH meter amplifier. If I take a pH meter amplifier, then the circuit that we can here one first thing is we select FET input op amp, The second is use the op amp in voltage follower mode. Use the op amp in voltage follower mode, so that we will explain this why one have to use in voltage follower mode in case of pH meter. This we will explain a little later. So, what you do is we will take the operation amplifier, then I will use the voltage follower mode, and the input I will connect pH meter. For example, if you take this pH meter, pH probe, we have taken this example of pH probe because pH probe got very high internal resistance of the pH probe. Internal resistance. So, internal resistance of the pH probe is very high, internal resistance pH probe is about 100 megohms. So, the internal resistance is very high. Now, if you look at the bias currents, they actually flows here as well as here, and the bias current that is flowing here, the bias current that is flowing into the inverting terminal has no problem, because they do not develop any voltage because there is no resistance here. So, due to this current I minus, there is no problem, whereas this bias current have to go through this to the plus input. Now, this bias current have to go through this 100 megohm resistance. So, when they go through this, the voltage drop will occur on this. So, essentially the bias current the bias current I plus, that is non-inverting terminal bias current I plus must flow through so I call it as RI input through RI. So, the voltage drop across RI that would be RI into I plus. This voltage, actually the current actually flowing like this. So, this voltage is minus. So, the net input voltage will be voltage of the pH probe minus the voltage drop that had occurred. So, assume that pH probe gives you 50 millivolt per pH. So, pH probe voltage is equal to 50 millivolt. We assume that pH probe voltage is 50 millivolt. Then voltage across RI, that is equal to 100 megohm, that is 10 power 8, that is 100 megohm into I plus, that actually 10 power 8 into I plus. Suppose if it is a 10 picoampere, then it will be 10 into picoampere. So, that will be minus 12, then that will be 10 power minus 3 volts. That is, here we have taken the I plus here I plus is equal to 10 picoamps. The bias current is actually very small. So, the error what you get is 1 millivolt. So, the actual voltage that is appearing at the input is 50 millivolt, which is pH amplifier, minus 1 millivolt, that is 49 millivolt. In this case, the error is very small. Suppose if I use the op amp which is having 1 nanoampere bias current, if the bias current nanoampere, then input voltage, then the error voltage, then the voltage drop, on RI, that is equal to 100 megohm into 1 nanoampere, that is 10 power minus 9, that will be 100 millivolt. Then net voltage at the non-inverting input equal to inverting terminal. Non-inverting terminal would be equal to 50 millivolt minus 100 millivolt, that is equal to minus 50 millivolt. This is a huge error. The input voltage polarity itself had changed. So, 100 millivolt error that comes because of the bias current. Of course, one can make a voltage follower in the following manner to take care of part of the bias current, because you can also have resistance connected here, and then we can have plus here, and if I know this is RI, I also keep RI here. Then if these two bias currents are equal, if this if the bias current of this and the bias current of this are equal, then output voltage will be 0. So, one can reduce the bias can reduce error in the voltage follower by adding a resistance RI in the feedback path. So, by adding a resistance equal to RI in the feedback path, one can reduce the bias current error. However, we can only reduce, we can't make it 0, because there are two problems in this. One, it is not easy to find out value RI which is equivalent to exact value of RI. We are not able to put it here, because the RI itself may be changing from transducer to transducer. So, it is not easy to for each transducer find the RI and putting it exact value, but nevertheless the order of magnitude error can be reduced by making more or less equal value of RI, by connecting equal value of RI in the feedback path here reduces. Even then you have error because of the bias current, because we know that even if I make it these two resistance equal, this and this equal, this current and this current may not be equal. So, because of the offset current, even if two resistance equal also you will have error. So, even if we manage to connect RI exactly in the feedback path, due to offset current. So, current there will be error, there will be an error voltage at the output. In that case, the error voltage would be RI into I offset. Normally, offset current will be one order magnitude less than offset bias current, since offset current is normally less by an order of magnitude, by a factor of 10, by a factor of 10, adding resistance in the feedback path, reduces the error. So, this offset current is a serious issue when the input internal impedance is very large. So, for example, if the if the pH meter amplifier, pH probe amplifier to work properly, then the RPH choice will be, you have resistance connected here, which is about 100 megohm, and then select FET input op amp, select FET input op amp. That makes the output error very small. For example, if you use 741 for this application, you will get tremendous amount of error due to offset current, and then also with temperature offset current will change and you will have a large temperature drift. That is why one have to worry about different types of op amps. There is like FET input op amp, low bias current, that is basically low bias current op amp, and then low offset voltage drift op amp. Like that is why we have very many different types are there. We will list it at the end. Now we are discussing about the error due to the offset current. Now since we are at it, that we also have to worry when we are selecting a low bias current op amp, when you are making a printed circuit board layout, one have to be careful about other current that is getting into the PCB, which is a much serious problem than this offset current itself. Let us see what is that, what is the care that we have to take when we are dealing with this low bias current op amp, issues in the low bias current op amp. The leakage current in the PCB will introduce large error. This one had to be aware of it. Now I can show you an example here. For example, if I take a normal dual inline package op amp, that you will have the arrangement like this, that is the op amp will look like this, that is pin numbers if you see. For example, we have this and we have two power supply terminals, plus and then minus, and then this is input, this is the output. So we have this is minus 15 volt, this is plus 15 volt. For example, if you take this is pin number 3 and this is pin number 2 and this is 6, this is pin number 4 and this is 7. This is the typical configuration most of the dual inline package op amp. Now physically they look like this, that you have 8 pins, 1, 2, 3, 4, and then another line you have this 8 pins. So if I take the pin numbers, assume this is 1 and then this is 4 and then you have 5 and then 8. This is pin number 8, that is you have here pin number 1 and then this, assume this is pin number 8 in the dual inline package, and the distance between these two pins is 2.5 mm. So the distance actually, this distance between the two pins is equal to 2.5 mm. Now if you see this one, we would have connected this is actually this distance, this distance between these two, 2.5 mm. Now if we connect the circuit, in reality we will connect this one to minus 15 volt, and then 5, 6, 7 will be connected to plus 15 volt. So we will take a layout and then we will connect this one to plus 15. Then this is 2 and the 2 and 6 are to be shorted. So I will connect 2 and 6 like this. Then I have to connect pin number 3 as an input. So I will take pin number 3 and take this out in the layout Okay, we will make the PCB layout. So, it has certain thickness. So, this is input voltage. Okay, this is connected to the I resistance, and this has a very high resistance, that is 100 megohm, like that. Now, in this case, and then this will be taken as output. This is taken as output. Now, in this case, this is made in a printed circuit board, and we said the distance between these two is 2.5 mm. And then even if it is a glass epoxy printed circuit board, you will have certain amount of resistance across this. It is not definitely infinity. For example, if it is a glass epoxy printed circuit board, then assume that this resistance, that is the resistance that is present between this and this, is 1000 megohm. This is a 1000 megohm. Now, this minus 15 volt, that is this minus 15 volt, goes through this 1000 megohm, then it actually goes like this, goes to the ground and completes the path. So, what really happens is minus 15 volt passes through this, and that current produces a voltage across this. Assume the pH probe voltage is 0, that is, it is a neutral solution. Assume that V input is equal to 0, R internal is equal to 100 megohm, R leakage, this is leakage resistance. R leakage to 1000 megohm. That means the minus 15 volt now is minus 15 volt is now divided between this 1000 megohm and 100 megohm, because this is 100 megohm, the internal resistance which is there, and that assume there is no voltage. Since there is no voltage here, we expect 0 volt at the output, that is, this is 0, and then this is having 100 megohm. This 1000 megohm, if I draw the equivalent circuit, that is actually here. That is here. So, you get this minus 15 volt applied to the plus input through this 1000 megohm, and then it is divided between this 1000 megohm and 100 megohm. So, voltage at the plus input terminal would be, because of this leakage resistance, because of the R leakage, voltage at the non-inverting input, that would be equal to minus 15 into 100 megohm divided by 1100 megohm, because you have 1000 and 1000 megohm and 100 megohm are in series. So, you get this, and that actually comes to be 15 volt divided by almost by a factor of because this 1 by 11. So, that will be you will have 1.4 volt nearly. So, roughly 1.4 volt error voltage appears at the input due to the leakage resistance. This is a serious problem in high impedance circuits, because now we are dealing with a very high impedance, and which is comparable with the PCB resistance. So, if I want use this then high impedance circuits with high resistances, so that the bias current high resistances, so that the voltage drop is less and the bias current effect also less, then I have to go for some technique to remove this power supply leakage voltage that is coming because of the limited impedance of the PCB material. Now, that is how to reduce this. How to reduce this error? This is where the guarding technique comes into picture. So, we use guarding technique to reduce the error due to leakage resistance. Okay, what is that? It is done in the guarding technique. So, the circuit looks like this. So, what you do is we will take for example, both the layout part. So, layout part and the circuit part. See, what is done is we have this 8 pin IC. Now, that is pin number 1, that is pin number 8. What we want is this. So, what you do is the circuit configuration will be same. So, 1 and then this is 6. So, 1 and 6 I join, then 3 is the input. So, I take 3, apply the input, test large resistance here. Then this point I take this the pin circuit board, extend it like this. Similarly, this part also I take this, extend it. So, this terminal, if you see now, this terminal which is the input terminal is guarded at both end sides. This and this are actually, it is not connected anywhere here or here, it is just extended like this. Now, this makes this error is that is the leakage is between this and this is not at all issue, because now what happens, we split this and see, we have now leakage resistance between this and this, we have a leakage resistance between this and this, we have leakage resistance between this and this. So, I call this is R1, this is R2 and this is R3. But then we know that output voltage is same as input voltage. For example, if this is 10 millivolt, then I know that this also 10 millivolt, and then the output voltage also 10 millivolt. So, this also 10 millivolt sitting. So, you have the, say if I name it that 1, 2, 3. So, the track number 1 is also 10 millivolt, and track number 2 also 10 millivolt, track number 3 also at 10 millivolt, that is track 1 is at 10 millivolt, track 2 is also at 10 millivolt. So, track 2 because input voltage same as output. So, track 1, 2, 3 all are at same. Similarly, track 3 also at 10 millivolt. Since all of them are 10 volts, so current through R1 or current through R2 and R3 are 0. So, current through R2 and R3. So, this resistance has no effect. Now, if we see R1, this is connected to minus 15 volt, to minus 15 volt supply. This is pin number 4, which is the op amp supply, which is minus, this is 2, this is 3, this is 6 and then 4 and this is 7, this is minus 15 volt, this is plus 15 volt. So, the pin number 4 is at minus 15 volt. So, R1 current through R1 is possible. So, now current, because this is at 10 millivolt, output is at, see the output is at 10 millivolt, we assume here it is 10 millivolt. So, automatically output also 10 millivolt. So, the output is 10 millivolt and this is minus 15 volt. So, there will be a current through R1. So, the leakage resistance R1 will have a current. However, the leakage resistance R1 sees one side, say minus 15 volt, and at the other side it sees minus 10 millivolt. So, there will be a current through R1. So, there will be a R1. However, this current will not produce any error at the output. There will be a current through R1 and that current actually flows through the output terminal. So, if you see this current minus current R, we can take this current actually flows through R1 and goes like this. But this will not produce error at the output because the output impedance is 0. So, eventually we say the current flows through the R1. This current R1 flows through the output terminal of the op amp. Flows to the output terminal of the op amp. However, this will not induce any error. However, this will not this will not introduce any error at the output. The question is why it will not introduce any error. Now, the answer is that the because the output impedance of the op amp is close to 0. The output resistance of the op amp is nearly 0. So, current flowing through that, current flowing through the output will not introduce any error. So, because output impedance is resistance is 0, so the current flowing through this will not induce any error. So, this system works well. Of course, we may wonder that if what happens if I connect one resistance between 2 and 6, because in this case we are directly shorted this resistance. Instead of that, if I connect resistance between 2 and 6, for example, here I add a resistance, then what happens? I will show in a separate figure to avoid confusion actually here. Because we said we introduce a resistance in the feedback which is equivalent to input resistance to reduce the bias current error. what happens? What happens if we introduce compensating resistance in the feedback path? Actually, that is a serious problem here, because if I put the resistance, then it looks like this. That is, you have op amp, I introduce the resistance here, which is equivalent to input impedance. Now, if I look at that in the layout part, then as we said, we will have pin number 2 and 6. Instead of shorting it, I have to put a resistance. Now, the distance between these two is only 7.5 mm. Even if I manage to put this resistance 2 to 6, then 6, this is to be connected here, then I will be following this, that is a guarding technique I will be using. Then I will be using here between these two the guarding technique, and this is connected to minus 15 volt, this is connected to plus 15 volt. Now, this is pin number 2, this is pin number 1, and this is 3, 4, 5, 6, 7, 8. Now, since this is very high resistance, the leakage resistance between this and this will produce a voltage at 2. So, this is R leakage RL. So, the RL will induce error, RL will introduce error at pin number 2. At pin number 2, and the guarding point has no use. The guarding point 3 is of no use. So, one has to be careful when we are using a resistance in the feedback path to reduce the offset current, because as is shown here, that using the guarding technique reduces the error due to the leakage and so on, but if you are using a resistance in the feedback path, then guarding technique also will not work. So, one has to be aware of this. So, the bias current or the offset current or the offset current drift is a major source of worry for a circuit designer, particularly if you are dealing with the DC voltage. And if your input signal is having a very high input resistance, then also the bias current is a serious problem, and one has to be careful in selecting the op amp for the particular application. That is why we have op amp which is called as a FET input op amp, which has a very low bias current, and similarly we have op amp which has a very low offset voltage drift. We will see more about these issues later classes. Thank you.